In this lecture, we are going to study about solar cell, its structure and characteristics. This is lecture 8 of unit 3 optoelectronics. You will see this is the diagram for a solar cell. A solar cell is a PN junction that can generate electrical power when illuminated with sunlight. They operate under photovoltaic mode. That is, if the diode is left on open circuit, an externally measurable voltage appears between P and N regions. This is the diagram for a solar cell, wherein we have metallic contacts at the bottom and on the top. At the bottom, the entire area is covered with metallic contact, whereas on top it is in the form of a grid, so that the light energy can enter and strike the PN junction. We have the p-type material and the n-type material over here. We have an external load across which the outputs can be taken. Okay, this is the diagram which shows you a solar cell, solar panel and a PV system. Now, a solar cell, it consists of a p-type chip on which a thin layer of n-type material is grown. So we have p-type, on that we have the n-type. The N region is heavily doped and thin so that the light can penetrate through it easily. The P region is lightly doped so that most of the depletion region lies in the P side. So the depletion region is mostly in the P region. It also consists of a glass cover and anti-reflecting coating. The front and back contacts are metallic contacts for the flow of electrons. Electron hole pairs are mainly created in the depletion region, that is the region between P and N. So the electron hole pairs are mainly created in the depletion region, and due to the built-in potential and electric field, electrons move to the N region and the holes to the P region. The movement of electrons and holes results in accumulation of charges on the two sides of the junction and produces a potential difference called photo EMF. If a load, for example like a bulb, is connected across the cell, a current flows through it. We shall see next what is the IV characteristics of a solar cell. The IV characteristics depends on the intensity of the incident radiation and also the operating point, that is external load of the cell. If the external circuit is a short circuit, then the only current is due to the generated electron hole pair by the incident light. This is called the photocurrent, denoted by IPH. Another name for this is the short circuit current, ISC. The photocurrent is related to the intensity of the incident radiation, IOP, by IPH is equal to K times of IOP, where K is equivalent to an efficiency metric that measures the conversion of light into electron hole pairs. When external load R is connected, it develops a voltage. This voltage opposes the built-in potential and reduces the barrier for carrier injunction across the junction. This is similar to a PN junction in forward bias. This forward bias current opposes the photocurrent generated within the device due to the solar radiation. This is because IPH is generated due to electrons going to the N side and holes to the P side due to the electric field within the device, that is drift current. The forward bias current is due to diffusion current, ID, that is current going to the P side, electrons going to the P side and holes to the N side. The net current can be written as I is equal to minus of IPH plus ID. So you can see in this diagram, the graph, on the x-axis we have voltage, on the y-axis we have current. It also shows dark current and also shows as the intensity of light increases, the current also increases. The useful power is given as P maximum is equal to, this is V max, V maximum into I maximum, and ideal power is equal to VOC into ISC. VOC is the open circuit voltage and ISC is the short circuit current. Fill factor can also be written as useful power by ideal power. So fill factor is about 0.65 to 0.8 approximately. So efficiency formula wise can be written as the useful power by input optical power. where the input optical power is also as light intensity into area of the solar cell into 100. As we already discussed, solar cell can generate about 0.5 to 0.6 volt. So essentially a solar cell is a device that can convert the light energy into electrical energy.